Okay, guys, it's time to start, and I just want to show you what I have posted on Kappa now so you can get started studying for the final, because today we finished the book entirely. The next class, Tuesday, we're going to have a final review. So to prepare for the final, I've all the homework, bonus, everything that's due, assignments and bonus assignments are already posted. And after today's lecture, you will be able to do them all. And it's a very short homework because I want to give you a lot of time to do the slew of practice problems that I have now posted on our course management system, so you can do them and over again with different numbers each time. So there's really good practice. And in addition to that, I know you all like to see paper and pencil worked out problems, so I will post some of those too, but they're not up yet. So now the final dates, times, you know where to go for that. Press right to our exam schedule. And here's, I know you all want to know what formulas you need to know and what will be given to you. So you'll have these too. The only three that are going to be given to you are the three that we've covered this one, and these two we'll cover today, but they'll be given to you. These are these non-parametric formulas for the non-parametric tests. Remember, the final is only post-exam 2 material. It's like a third hourly this time. So you really don't have that many formulas to know because it only covers material from chapters 39, starting with the re-randomization, which didn't have any formulas, then the transformation of variables, so you need to know how to compute those confidence intervals back on the original variables, those asymmetrical confidence intervals. And then you need to know the three forms of the logistic regression model and how to compute odds and odds ratios. And z and chi-square tests, just really, you're going to be given the standard error for the z test. You'll be given the chi-square statistic. It's just looking it up on the table, basically this. You need to know the degrees of freedom. And these ranks, these last three come from the non-parametric tests we're doing now. So that's pretty much it. And let's see what else. So if we go to the exam schedule right here, as you know, this final is not really a final. It's a midterm, a third midterm. In the last, you're allowed 3 hours for it, though. Here's your schedule, where to go. And you see it's all 3 hours. You're allowed 3 hours here. You guys are going to be taking it Wednesday. If you're in class or in the online section, you're going to be taking it Wednesday afternoon in Follinger. And if you, anybody in the L1 section or the online section has the option of signing up for this conflict right here. The other sections have to arrange their own conflicts. Okay, so you can take it Thursday afternoon. If you choose to, you don't have to show me anything. I'll have a conflict sign-up sheet on Kappa. So it only covers material after exam 2, 90 minutes long. So the other thing I just want to show you on the calendar is where we are now, so you can see all these we're right here. And so our lecture will be posted right after class. And so you have this R bonus assignment to do if you want to do it. It's just doing some of these non-parametric tests in programming R if you want to do that. And, oh no, it's this one right here. You have a lot of time to do it. This one was the one I posted a long time ago. So if you're into doing these, feel free, but don't feel obligated. They're just for bonus points. And this homework is very short. It covers what we do today. So any questions on anything before we start? And I'll be sending you emails, of course, how to study, and like I always do. All right, so let's go to the document camera and finish up here. So, all right, here we are today. Now, so what we're going to be doing today is an extension of what we did last time with these have hard, unintuitive names. Okay, so last time we did this Whitney-Mann, what was it even? Wilcoxon-Mann-Whitney rank sum test. If you recall, let's just remember quickly what we did here and why we did this. It's a non-parametric test, meaning that we couldn't use any of the assumptions about some underlying distributions. What we did instead, and we couldn't do that because we want to compare the means of two groups. It's the non-parametric equivalent of the two-sample t-test. Okay, that's what we did here. We said we couldn't do a two-sample t-test. Why? Because we had some assumptions violated. The main one being that these small samples didn't come from a normal distribution. They came from this is an actual example that we do before we give any exams to masses of people. We give them early to a handful of people, and we look at their scores, and we say, we have two versions. We want to make sure that they're the same level of difficulty, it's very important not to shortchange students, and I've seen it happen all the time, giving two versions of the exam and they're not the same level of difficulty. So one cool test to make sure they are, even if you have small sample sizes, is to change these scores because they're not normally distributed. We can't do a two-sample t-test. We change them to all these values, to ranks. And you can see why this is useful. So this person who got an 11, these are real scores. This person who got an 11, we want to see if these are the same level of difficulty, right? You don't want to get a harder version. So this person who got an 11 on an exam which has a lot of multiple choice was going to get an 11 on either exam. Clueless person who didn't even come to class, had no idea what was going on. There are always people like that, right? And so whichever group he was in, he was going to create a very strong effect. So instead what we did was we ordered these numbers. We got rid of these values and just did a rank ordering. And then did statistics on the rank. We called it the rank sum, and we saw the rank sum and the U statistic. Now we're just going to do an extension of this to three groups, which is what happens on the final. These are midterms have two versions. Our finals have three or more. So here's an example. So now we have the same situation, okay? So you can think of this as the non-parametric equivalent of ANOVA, where you have three or more groups, so you can't do a Z or T test, right? It can't be a Z or T because you can't boil down the difference to a single signed number. We'll see that as we work through the statistic. But basically, so we can't use, when we have three or more, we can't just do what we did before, and we already saw we can't use a T, we also can't use a Z with more than two groups, okay? So that's out. So what do we usually do? It's a non-parametric version of ANOVA for comparing three or more group means, okay? But it has this really big advantage of not needing the underlying assumptions, not needing the assumptions of underlying normal populations. We don't need that. Okay, we really need that for ANOVA. Remember, the errors have to be distributed normally, right? Around zero, the errors are normally distributed, independent, identically distributed with zero mean and variance all the same. So what that means with groups is that each group, the errors are distributed around their group mean, and it means that they all have to have underlying normal distributions, or roughly so. And we don't have that here. Why? Because our exam, I've never given an exam where there's a normal distribution because this is stat. These are introstats, and hopefully I want most people to do well in the exams. So they always have this long tail. They're capped at 100, and so this is the type of distributions we always have. All right, so what are we going to do? So let me just write that. We can't use ANOVA comparing group means. That's basically the F test, right? Can't use the F test because our exam scores aren't normal. They look like that. That's what they look like. Okay, so what do? We're going to start off exactly the same way. This is easy for you guys because last time we spent a lot of time talking about this, but it's just a slight tweak on what we did last time. So we're going to combine all the three groups into one ordered list from smallest to largest. Okay? And then we're going to assign each one a rank, an integer between, there's 16 of them. There's, 5 here, 5 scores in group A, 5 in group B, and 6 in group C. And these are the actual, pretty much the actual exam scores when we did this once for a final. Okay, for their 3 versions. And we want to know if they're the same or not, okay? So what we do is we combine these all into one ordered list from smallest to largest. And these are the ranks. So we replace each of these values with integers between 1 and 16, because there's 16 numbers. Now what happens in the case of ties? We have a tie here and a tie here. So instead of saying 1, 2, 3, 4, and get 5, 6, we take the average between 5 and 6 right here. So we give them the average, so they're both 5.5, so we still end up with between 1 and 16 here. All right, so that's what we do, so let's do it. You don't have to write this whole thing out. You can do it in your head if you want. You can just say, okay, I see this is the lowest, so that is a rank of 1, this one. And you see that's the highest, so that must be 16, etc. But it's easier for me to just, and I have so many numbers, to just write them like this. So now I can just look down here and I say, okay, 10's 1, 60's 4. And remember, I'm going to be adding these up. These are going to be rank sums like we did before. That's a rank sum of the A group. So that's 1 plus 4, and then 70 is 5.5, plus what did I get for 80 is 8, plus 16. So we're going to add all those up for this one's rank sum, and that's 34.5 for these 5 numbers in group A. That's the sum of their ranks. Now we'll do the same for B, etc. So for B, what do we have? We have 3 plus 70 is 5.5. 81 is, tell me if I make a mistake, 9. 85 is 10. And 95 is 13. Okay? And I add those all up, and I got 40.5. Okay? 3 plus 5.5 plus 9 plus 10 plus 13. Let's do the last one. And the last one is 2. I'll just write it down because I have it here. 2 plus 7 plus 11 plus 12 plus 98 and 99 are 14 and 15. And this has 6 numbers. We add them up, and this rank is 61. All right. So those are our observed rank sums that we actually got. Now we have to think about if they really were, when the null is true, if they were really drawn from the same, there's no difference in, what we're interested in is this question. Were all 3 versions of the finals equally difficult for all types of students? That's what we're interested in. Not just whether their means are the same, like in a 2-sample T or a ANOVA. We're not just comparing means. This is stronger than that. Because what I really care about is not just that they have the same means, but I care about that they're the same level of difficulty for all the students, for the lower students and for the higher students, not just that the averages are the same. So it's a stronger no, and it's more what I'm interested in this situation. Okay, so this is what we observe. Now we have to think about, but before we go any further, there's a lot of arithmetic here. Let's check that we didn't make an error here, because it's so easy to do. So you want to check that these 3 sums add up to this. Why? Remember what this formula comes from. This is the formula for adding numbers between 1 and n. And remember how we talked about how Gauss figured this out as a student really quickly? he said, okay, let's do it here. We had 16 numbers. First, let's do it. It's 16 times n plus 1 is 17, and then we divide by 2, and we get 136. So we want to check if those three numbers really add up to 136. And you should do that for sure on an exam. So just to make sure you didn't make a mistake. So we're asking, do they add up to 136? And they do. Okay, so we know we didn't make an arithmetic mistake. Now, why does this work? Just so if you should, this is a formula you should know. It's a really cool formula. And think about why it would work in this case. All right, do you see how if we take 1 plus 16, that's 17, right? Whoa. 1 plus 16. 2 plus 15 is 17. 3 plus 14 is 17, etc. And you go all the way down to 8 plus 9 is 17. So you really, even when you have, okay, so usually we have a 5 and a 6 here. So that would be when we say 4 plus 13 is 17. Here we go. If they weren't tied, it would be 5 plus 12, 6 plus 11, right? Did I do this right? 1, 2 plus 5. I'm getting confused here. 3 plus 14, 4 plus 13, and then I'd have 5 plus 12, 6 plus 11, 7 plus 10 is 17, and 8 plus 9 is 17. So how many of those do we have? N of those. So we have n over 2 of those. So we have n over 2 times n plus 1. So we have 8 pairs, 8 of 17. So that's the way you can remember the formula. And another way you can remember this formula is this is n times the average of all of them. The average is between 8 and 9, right? Isn't the average between 8 and 9 8.5, the middle number? So another way you can think of it as n observations times the average. So any questions on this? This you have to know. I'm not giving it to you. So that's why I'm giving you a lot of ways to remember it. So you can easily remember it as, look, when we find the expected sum for each group, that's what we're going to do. If the null is true, what we want to figure out is the expected value for the sum. The expected value for the sum when we get this formula right here. Now remember, the expected value, we had this way back at the beginning, for the sum of n draws from a box that has some average is equal to n times the average of that box, right? And that's the same thing we're doing here. You could think of this right here as the average, and we're taking all n of them, so it's n times the average. Now, for each particular group, like for this group, to find, we got 34.5, but we would expect to get its sample size times, if we draw 5 numbers out of here at random, and remember, we're imagining the null is true, that that these are just random draws from this set. So we have n numbers from here. We'd expect the average, we'd expect it to be 5 times 8.5, 42.5, and we got 34.5. So let me just make sure you understand this. This n sub I, this little n, is the sample size for each group. Okay? And this big N is the total sample size. That's the total sample size. So in this case, that's 16. All right? And then what's this n plus 1 over 2? N plus 1 over 2. Do you see what that is? That is just the average. That's 17 over 2, 8.5, which is the average. So it's just the average, or the mean. of integers, of all numbers, integers between what? Basically 1, 2, 3, all integers to n. Okay, so that's what that is. So another way to think of this, if you don't want to remember what Gauss did, is to just think it's just our usual formula, n times the average. That's what they should, when you have the whole box, right? And then all the population, and then for these individual ones, what would you expect when you only take here the sample size for n sub 1, here, n sub a we'll call it, is 5, because we have 5 numbers. Here, n sub b is 5, and here, n sub c is 6. So to get the expected value, these is what we observed. These are observed rank sums. But what would we expect under the null? What would we expect under the null? And this is what we're doing right here, our expected ones. So these are expected ones. This is n times the average right here. You know, right? 5 times n plus 1 over 2 is 17 over 2, and that's what we get. And the next one, this is also 5 times 17 over 2, because it also has a sample size of 5. So that's also 42.5. And what's this one? This one is 6 times 17 over 2. So this one has a sample size of 51. All right, so that's where we're at so far. And we have these observed and expected. So now we did this exact same thing, these same formulas and everything last time. And then we just said, okay, we can do a z-test, right? We said observed minus expected over the standard error. We did that last time. But now we can't do a z-test because we have 3 groups. So we have to do basically a chi-square test. This, in fact, is a chi-square test. It's called the H statistic, just because the standard in this context is just called the H, but it's distributed as a chi-squared with degrees of freedom. The usual, when you're comparing 3 groups, what would it be? The degrees of freedom for a chi-square test is what? The number of parameters minus 1, which in this case is the number of groups minus 1. So that's 3 minus 1, which is 2. So we know that. It's going to, now, it probably doesn't quite look like a chi-square test to you, but I don't know if you're interested in me, if you do the algebra here, do you want to see it now, or do you want to, maybe we should go through the test, and at the end I can show you why it's the sum of z-squareds. We already did the z-test. Let me just pull it up somewhere else so you can remember what it looked like. We already did it, just so you can see it's really similar to what we did before. We did it back here. All right, so just compare. So we have these rank sums. This is what I'm comparing to. This is z, the observed rank sum minus the expected rank sum over the standard error. And this is what we said was the standard error, and it's going to be given to you. But I showed you, if you didn't have to pay attention, you don't have to know, but I showed you how it was derived, where we got the 12 from, and how this made sense. And now this basically, if you square this, because we want the sum of z-squareds, and multiplying by this is the same as dividing by its reciprocal, we'll get the same thing. So I don't want to go into the math details now. Anybody wants to see it afterwards, I can post them. But I just want to keep with our logic of what we're doing here, because that's a sort of mathematical detail. And what we really want to understand here is these differences, why we have to square them and sum them. And instead of what this means here, that our test statistic, when we have 3 or more groups, can't be a z. Why? So you'll see that when we do this, all right? So let's compute the test. But before we do that, we should really state our null and our alternative. So our null, we said what we're trying to figure out is were all versions of the final equally difficult for all types of students. That's the same as saying that that the null is all three versions, all three groups came from the same distribution. And we don't need to know that distribution, but that's what we're testing. They came from the same distribution. And as we saw last time, that means that this test can detect even when they have the same means, can still find differences in the distributions. So if it still can find differences in the distributions, which makes it really great for what we're doing here. Okay, and now the alternative, and that's the same thing as saying, in colloquial terms, were all versions of the final equally difficult for all types of students. All right? And the alternative is, no, they're not all equally difficult for all types of students. There's at least one segment of students that it's different difficulties for, which is the same thing as saying that not all three groups come from the same distribution. At least one of them is different. All right? Either easier or harder. That's the idea. So now we're going to compute this H statistic, which is like a chi-squared. So let's see how this is given to you. Let's make sure, so don't worry at all about memorizing this. This will be given to you along with the other standard error one. So this is your second one that you're going to have, second formula that you'll have on the final. All right, so let's go ahead and do it. So we say 12 over 16 times 17. And then what are we doing? We're summing up for each group. What are we doing? We're taking this observed sum minus the expected one. So these two numbers, the difference in squaring it. So that's what we're doing here. So we have 34.5 minus 42.5 squared, and then it's over its sample size. And its sample size is 5. So now we'll do the next one. And the next one is the 40.5 minus 42.5 squared over 5. And the last one is 61 minus 51 squared over 6. So that's what we're doing. All right. So what I want to show you now, instead of just working it out, I want to show you these differences in here. And then you'll understand why we have to square them. Okay? So let's do that. So our differences are what? 34.5 minus, that's minus 8 squared over 5, plus, the difference here is minus 2 squared over 5, plus this difference is 10 squared over 6. Now, the reason I want to do this, it's a good check for you. Look what happens. Before we square these differences, they always add up to 0. They always add up to 0. And this is, you've seen this so many times in computing a standard deviation, and summing squared differences is a feature of so many of our tests. And the reason we didn't have to do it before, when we just had two groups, let's check back to what happened then, these, once you distribute this out, are like the z squared. And we didn't have, remember chi-squares, the sum of z-squares, independent z-squares. These aren't, but that's another story. But I just want to show you that these, we have to square these z's, and we didn't before. Why? Let's remember what we did before. what we did before here with the ranks, okay, is we did this, okay, so we got this z, and do you see we didn't have to square them because here's the zb, and here was the za. We have the observed minus the expected over the standard error, observed minus expected over standard error, and we get, sure, if you sum those differences, it's 0, but we just need one of them. We just need one of them because the other one's the opposite. So we don't have to add them together. We just take one of them. This test just takes one of these and gets a z-score for it, and then it does the other and it gets the opposite z-score. So they have opposite z-scores, same p-value. And that's also what happened when we did the same thing with the U statistic. So, and it's always what happens. That's why with 2 samples, you don't have to square them. Because the difference is always summed to 0, but they're going to be opposite of each other. So knowing one's the same as knowing the other. But now, knowing one isn't the same as knowing the other, so you can't just, you have to square them. So we're getting a measure of how far they are. These are measures of how, when the null is true, we'd expect for these, and this is just a difference of how far our sample landed just by random chance from the null. And that's what a chi-square statistic is. So, let's, when I show you the chi-square statistic, I want you to think right away. Do you think we're going to reject the null or not? It's going to be so obvious. So, when I add these up, I got only 1.344. Okay? 1.344. So, remember what the mean of the chi-square distribution is. What is it? The mean of the f is 1, and the mean of the chi-square is what? Well, the null is true. When nothing's going on, what's the mean of the chi-square? You know this. What? Yes. It's degrees of freedom. It's degrees of freedom, which we know is 2. Right? So let's just picture this chi-square with only 2 degrees of freedom. Right? It's not going to be symmetrical yet. We've done this a lot. Let's just do this, and then we'll check. But I just want you to get the intuitive picture. So you have this chi-square distribution that's all positive. It's the sum of squares. It has this long tail like this. All right. And we're saying, you should just know, let's write it down here just so you remember, that the mean of chi-square distribution when the null is true, that's important, when null is true and nothing's going on, is equal to the degrees of freedom. Sorry, that looks terrible. Is equal to the degrees of freedom. In this case, it's 2. So, what does that mean? It means that the mean, I don't know, the mean with, I'll just put it about here somewhere. So that's going to be the mean. And look what our statistic is. So there's a lot of area this way. That's the mean. And our statistic, our H statistic, which is like chi-squared, is right here at 1.344. So what does this mean? Is it consistent with the null? The null says, when nothing's going on, this is what you're going to expect to get. If the differences are really big, we'd expect to be way out here. This is so consistent. It's going to be over 50%. I mean, we don't really have to do a test, but pretend just to keep with the logic of how we usually do a test. If it was way out here, we'd say, that's pretty far from what we'd expect. These differences are going to give us a big statistic. We expect to get, how likely is it? So we compute the p-value. So then we'd have to, with the degree, we'd have to compare, we usually compare our stat, which would be H, and we'd compare it to see if it's greater than or less than the critical value of chi-square at some, with 2 degrees of freedom at, if you want to do 5%, we could do that, at alpha equals 0.05. So we look at our table, just to do this and so you get the picture, because you will do this on the final. So we look at and it has 2 degrees of freedom, right? And here's our picture of the chi-square. It says it's starting to look normal because they did one with more degrees of freedom. But at 2, it looks really asymmetrical. And here is, at 5%, our critical value. So we can draw that. This keeps getting smaller and smaller and smaller. I'm sorry, I do it so badly. All right, so we have 2, 4, 5, 6. It's about right here. So this is 5.99, and this is our critical value at 5%. What does that mean at 5%? Sorry about that. What does it mean at 5%? It means that when the null is true 5% of the time, even when the null is true and all versions are the same, you're going to get the statistic that's 5%. Our actual p-value is this huge thing. Why don't we look it up and see what it is? I don't even know what it is. We can look it up on our p-value calculator, but it's probably over 50%. It's not symmetrical, so I know this doesn't divide it into 50% pieces, but I bet it is somewhat over 50%. So let's check it out, and we'll do that. All right, so we'll go to our p-value calculator, and we have a chi-square distribution. Degrees of freedom is 2. Our chi-square statistic, their H statistic, which is a chi-square, is 1.344. So put that in, 1.344. And now we just want to see what our p-value is. So it is 51.07%, and there we have it. And let's see, if we wanted to get 5%, you can see where the 5.905 there. And with degrees of 2, we'd have to compute a chi-square, and that's 5.99. There's the 5%. Okay? So it's extremely consistent with the null, is our results. So our conclusion is what? So let's just fill it like how we usually do it. We compare our test statistic to some critical value. If it's bigger, we reject the null. It's smaller, so we cannot reject the null, obviously. The null is, we completely agree with the null. So we cannot reject the null. Our data is extremely consistent with the null. It strongly agrees with the null. We assume the null, but our data is very consistent with the null. Consistent with the null. And you know, this is a good thing. I was delighted. This always happens because what I'm testing is whether I want it to come from the null. It's not like I want to prove something, get a small p-value. This is a situation where I absolutely want it to be a random selection from the same exam. So I am totally delighted when I get these kind of results. And that's what I'm aiming for here. Okay? You don't always want a p-value less than, you don't want to, you would hate it if it was. It would mean that one exam was much harder than the others. Okay, so that's the idea. And any questions on that before we move on and go to our last non-parametric rank test? All right, so we're going to finish early, I think. So we're going to do this, continue here, and this is the rank non-parametric. The non-parametric tests that we're doing right now in this section are all rank tests. So this is the non-parametric equivalent of a regular correlation coefficient. So what do we have here? So we have, imagine that we have these 7 pairs of numbers between, these are just 7 pairs of numbers. Continuing with our exam analogy, we could say this is the first and second score of 7 students on exam 1 and exam 2. Okay, 7 observations, and we have 2 variables here. So we want to, now, we might want to change them to ranks for many reasons. Lots of times it's more informative, that's what we want, but also because before we did re-randomizations tests, I mean, these aren't going to, if this doesn't follow a nice linear curve, we have other things we can do with it, we can do data transformations. Let's say that doesn't work. We can do a re-randomization test, but let's say you didn't have a computer simulation, you didn't want to program your computer to do that, you didn't have that handy. One thing that's actually people do a lot, and especially in cases like this where they're clearly not normally distributed exam scores, is they change them to ranks. And the beauty of that is then it's very easy to compute the correlation coefficient on the ranks and to do probability, either exact probability distributions by permutations or normal approximations. So let's just do it. All right, so we're going to change to ranks here. And if we change them to ranks, how do we do this? So we look here, I already ordered them so that the x variables go from smallest to largest. I've already done that. So if we look at this, we can just rewrite this as 1, 27 is the smallest, 2, I just put them in this order, 3, 4, 5, 6, and 7. All right? So that's our first variable. 1, 2, 3, 4, 5, 6, 7. So now we just want to order these, the second variable. So when's the smallest? 40 is the smallest, so that will be the first one, 2, 1. 45 is the second, so that's 2. I'm just ordering the y's. Do we have any 50s? Where's our third one? 61 is the next smallest, right? After 61, is it 70? Yeah. Then 79, so that's number 5. 82 is 6, and 99 is 7. So what we do is we take any set of 7 numbers, 7 pairs, are going to be converted into pairs of numbers where the numbers are all between 1 and 7. So we can write these down here. So we have 1, 2, 2, 1, 3, 4, 4, 3, 5, 7, 6, 5, and 7, 6. So it's very nice because now we could even graph this. It's just so easy to see what's going on. We could, if you want to compute the correlation coefficient by scratch, we can do that. And we do it, once we get them in these ranks, we do the correlation coefficient the way we always do. We might as well do it. It's pretty easy here. We just convert to z-scores. Remember the correlation coefficient. Remember, so what are we going to say? So the R correlation coefficient is going to be basically just the sum of zx, what we usually do, zy over n once converted to ranks. Once values are converted to ranks. Okay? So it's just going to be exactly the same thing as we always do. So here we'll get the z-scores. So first we'll just take see it's very easy now because we have numbers between 1 and 7 instead of those numbers. So we can just see the average for the x is 4. And of course for the y it's going to be the same thing. They're the same set of numbers. And the standard deviation for the x is 2. It's very simple to do if you want me to. And the standard deviation, excuse me, I put a little bar for no reason. And the standard deviation for the y variables is also 2, because they're the same set of numbers. Does anybody want to see that worked out? We've done it so many times, the standard deviation. Okay, so we've got that. Now, we're just changing them to z-scores. So you say, for x, you'd say 1 minus 4 over 2, right? And that's negative 1.5. And then you'd say 2 minus 4 over 2. That's negative 1. This would be negative 0.5. 4 is right at the average, 0. And this is a half above, 1 and 1.5. And you check again. These deviations are going to sum to 0. All right, and now we'll do the same thing with the y variable. So here we say 2 minus 4 over 2. So we get negative 1. The y variable is 2. Now this is 1 minus, what do we have here? 1 minus 2, don't we? 2 minus 1. So this is negative, 2 minus 4. Okay, so this is negative 1.5. And this is 0. They're the same numbers, just rearranged, right? And 3.5, 3 is going to be negative 0.5. And 7 will be 1.5, right? 1.5. And 5, these are 0.5. And this is 1. Do they all sum? Yep. They all sum to 0. All right, so now, so what do we have here? We do their products. We have 1.5, 1.5, 0, 0, 0.75, 0.5, and 1.5. So that's their products. Okay. So we'll add them all up, and so our observed R is the sum of all those products, which is 5.75 divided by n, which is 0.8214. That's our observed R. Any questions on that? Do you want me to graph it? No, I don't want you to either. Okay, so the idea is what? The idea is that the null, our population correlation is 0. We just happen to see this non-zero population correlation. So in other words, we have two sets of numbers between 1 and 7, and just by random pairing, we happen to get 0.8214. Now, we could figure out exact probability tables. What's the chance of doing that? Like we do for all the other, if you have a small data set, you can figure out exact probability distributions. But with a large enough data set, like we have 7 or more pairs, the distribution of R under the null is approximately normal. So we can just use a z-score and a slightly simpler z-score because we know the distributions here. We know the standard deviations. So it's, remember our other one was, it's an easier formula than our usual one, which our usual one was more complicated. It was what? The square root of 1 minus r squared. And you don't have to memorize this. This isn't going to be on this final, over the square root of n minus 2. But we have such a simple set of numbers that we know what they are. They're integers between 1 and 7. We know the standard deviations. So we can just use the simpler formula right here to compute our z-score. So we can just say our z-score is the observed minus the expected, which is 0.2184, minus what we'd expect under the null, over 1 over the square root of 7 minus 1. And I did that, and I got 2.01. So that is our z-score. And then we can just say, okay, so as a z, we know 0, 1, 2, 3, -1, -2, and 3. And now as this r under these conditions, r is bounded at 1 and -1, so it's not really appropriate usually to do this, but in this circumstance, when you just have these integers that are very well defined, I know it's not going to go all the way out there, but for our purposes, the normal curve goes on forever and r is bounded, but this is a good approximation. And look where even a high r, like that, what does it translate to? That translates in terms of a z-score to 2.01. So that is right there. As an r, we'll do an r-axis. So this is a z-score. We'll do an r. As an r, we have 0 there. And right here, as an r, this is where our 0.8214 matches up. And it's, as a z-score, it's 2.01. Okay. So, what's going to be, let's figure out the probability. So now our null is what? Two-sided, our alternative. So that means that we didn't specify whether it was going to be positive or negative ahead of time. So we should do a two-sided test. So we should look at the area between z equals 2.01 and z equals negative 2.01 and get that, and this will be our p-value. How likely it is to get that far away. So we can look up that. Okay, so this table doesn't really give 2.01. It's somewhere between 95.45 and 95.96. So I looked on the p-value calculator, and I got 95.6. That means there's 2.2% here and 2.2% here. So our p-value is 100 minus 95.6%, which is 4.4%. All right. So if we're going to use that cutoff of 5%, we would reject the null. So we would reject the null that it was a random, these numbers were randomly drawn from this population of just integers between, that the correlation is 0 between the two of them. And we reject the null and at 5% significance level. And conclude there's good evidence that the probability, if these were 7 students drawn from a big population or something, and there's good evidence that their exam scores are correlated. I hope there would be good evidence that their exam scores are correlated. I mean, I tried to pick these as real students. So reject null at 5% significance level and conclude that R in the population, rho, it's just too hard to write because it looks like a P, that the R in the population is, we can't say it's not 0. We have good evidence that it's not 0. We can't conclude that. We assumed it. That's a bad way to put it. We conclude that we have good evidence that R in the population is not equal to 0. What kind of evidence do we have? We say if it was 0, it's just like, a legal argument. If they were innocent, at some point we say, hey, we just have too much evidence. We're going to convict. Okay, so with too much evidence, we can't say for sure at all. We can just say that it's unlikely that it's the probability of, if it was really no correlation, the probability of getting such an extreme test statistic, an R of 0.8214, if if there really was no correlation, is only 4.4%. That's what we're saying. All right, now, but one thing that I think we should really talk about that I realize I neglected is this cutoff of 7. Why am I even using this, or why am I all of a sudden switching to these z-tests that I said we couldn't do? What's the justification for that? We talked about it the first hour, but I realize I didn't emphasize it now. So what we're doing here is we have these 3 rank tests, non-parametric rank tests, right? And we did this one last time. This is the Wilcoxon-Mann-Whitney. It's the parametric equivalent of the 2-sample T. Now, I say if there's a small sample, what we have to do is use these exact probability distributions. And we did that last time. We talked about that. We have to use these exact probability distributions. For this one, for example, if I wanted to test, let's say we got a correlation coefficient of 1. We got a correlation coefficient of 1. How would I figure that out exactly? Right? Pretend we did that. Pretend we drew from 7 numbers and I got 1, 1, 2, 2, 3, 3, 4, 4, etc., all the way to 7, 7. Now, how would I figure that out exactly if I didn't want to use the normal curve? What I could say is what? How many possible permutations, if you want to do it exactly, you'd say, how many possible ways are there to pair up 7 numbers like this? You'd say, okay, once I got, so I have 1, how many possibilities are there? 2, 3, all the way up to 7, right? So it's, how likely is it that I'm going to get a 1 in here, an exact 1 in here, and also get a 2 in here, and da-da-da. Well, there's 7 possibilities for the first one, times 6 for the next one, times 5 for the next one, times 4, times 3, times 2, times 1. So it would be 7 factorial, right? Which is what? $210 times 24?
5,040.
5,040. Good. Great. So it would be 1 out of 5,040. So if we did 2-sided test, it would be 2 out of 5,040. Okay, so this is, and you could do it for all of them. So that's what these tables that you look at are. So this huge advantage of doing these non-parametric tests is not so much that is when you can if you want, even if it's greater, they go up to greater than 7. I'm just saying for the purposes of this course. A lot of them end at 7, but they go up much higher, and you can just look them up. These are very common tests. You can just, on software, you can just click a button, or you could look them up and get all the tables. We did that for the U statistic, right? But, so let's write that down. So that's why it's very useful. So because we can use for these, we can use exact probability distributions. And they're for small n. They're not going to go up to, but this is an arbitrary cutoff that I chose just for our class, because our tables go up that far. Okay, so that's a huge advantage over our re-randomization tests, which is another type of non-parametric tests we talked about before. Doesn't rely on underlying distributions, but there we're just resampling our same data. So you're not going to have tables on that. You have to actually program the computer to do that through simulations. So that's another, but this class of rank tests, they have good tables for it, and that's why they're so useful. Now, why all of a sudden that just a low number like, usually we have to get much higher for the central limit theorem to kick in. Why, for, how can I say this, for n greater than or equal to some small number like 7, why can we use these z-tests? And this is a huge advantage too. We can use z and chi-square stats, right? Z and chi-square stats. We're not going to use t and f's because we're not estimating any standard deviations. We know the standard deviations. We have the numbers. So for n greater, we can use z and chi-square test because, why? Once our data, that can be completely wild data, is converted to integers between 1 and n, we have a very nice distribution, an even distribution, a uniform distribution. We have a close to normal distribution, not a weird distribution. So the central limit theorem is going to kick in much sooner. We saw this, that if you have if you take the sampling distribution of the sum, which is what we're doing, or the average of n draws from any distribution, it can be completely wild with enough draws, those statistics, the average, the sum, the percents, will become normal. But it takes a lot of draws to do that, a big N. If you have a very skewed distribution, we have this beautiful, close to normal distribution, regular distribution. So we have, because once converted to integers, once it's converted to ranks, that's ranks, we have a close enough to normal, we have what? Data in the ranks that's close enough to normal that the central limit theorem kicks in really quickly. So we can use z-scores on the sums, right? And then, so these are really, really cool tests. And so let's just make sure we read the summary here, and then we're almost done. So all the parametric tests we've done assume that we're dealing with normal populations or large enough samples of the statistics, that the statistics follow normal distributions. Okay, now if we don't have normal populations, we can sometimes transform the data to look more normal. That's what we did when we had data, just remember, that was right skewed. We powered down. Remember, we wanted to bring this in, so we took logs and square roots and logs. And when we had it looking like this, like our exam scores, we powered up. Anyway, so that's what we did. We did those transformations in part 13. That's going to be on the exam. Also, how about with logistic regression? That wasn't normal either. So we did what? We put it into a form where our parameters were normal once it was in the log odds form. So we can transform to look more normal, or transform parameters. Right? So their distributions look more normal. Because we ended up using z-scores for those. Remember z's? We never use f and t's for those. So, okay, parameters. So this is not important. I'm just trying to be too exact here. I'm getting anal, sorry. But, sorry, bear with me. Sorry. Basically, this whole thing that we're doing in this, that exam 3 is on, is dealing with beyond the usual intro course and saying, okay, now we don't have these normally distributed errors. We don't have these linear, they don't look linear, so what can we do? So these are numbers of, first we did those re-randomizations, then we did those data transformations so that we could use normal, so we got normal curves, and then we did that logistic regression, then we finally were able to use the z-test on those slopes because the parameters in the log odds form were normal. But when all that doesn't work, when it all doesn't work, we have these non-parametric tests that transform the data into ordered ranks and then compute a statistic based on their ranks. Or, like we did before, or we do computer simulations by these resampling methods, or we can use resampling methods. So that's what we've done this whole time. We can use randomization tests. Okay? But this part is about the rank tests. And these are the ones we did, and that's sort of the summary here. So, long-winded summary, sorry about that. Hey, did anybody do the extra credit? Did anybody do that little bonus thing that remember that? If you're not interested, we don't have to do it, but didn't we have something that we were talked about? Where was it? I thought that I asked you to do something. This, on page 217. How about if you just think about it I got an idea. Everybody at home watching, you guys here, you should fill this in and do this. Just try to do it, and then I'll post the solution to it. It's fun. So this is not for fun. This is for when you turn in your notebook for bonus notebook credit. Because I'm going to tell you what pages you have to fill in for bonus notebook. So I'll list this as trying it on your own, but I'll do a few solutions. Okay? All right, it was a fun problem. And I think will help you understand rankings. So why don't we do that from bonus notebook credit? And I'll tell you, we've done almost every page in here, and so this should be filled in too. All right, so that's it, and I think it's time to go. Any questions? Any questions at all? No one has a question on any of this? It's kind of complicated. Okay. See you.